All right. Hey, so if you haven't seen me before, my name is Will Chiefbein. I'm one of the TAs for STA 371G. And today we're doing the R review session, which will be mostly covering the stuff that's on homework 7. And we are changing the format a little bit. It's not the exact same data set, but it's pretty much the exact same methods. So just apply the same thing that we just did here exactly over there. I mean, it's pretty much the same code. It's just you're going to have to actually interpret that particular data set, and you're going to need to just run out a different data set. That's really all there is to it. Okay, so how many has actually started on homework 7? 2? All right. So homework 7 is all about time series, as you might guess from what the exam is. I mean, what the lessons have been over. And so today, the homework's over the Johnson & Johnson's earnings, which is a data set, and you'll see that it's got a nice time series. So today I'm pretty much doing the same thing on a data set that's already in R. So if you load up the library forecast, I'm hoping you'll just run along with me. I hope everyone has their R session going. So today we're just going to be working in forecast this air passengers. And so I'm on a new computer here, so I don't have library forecast, but if you don't have a library, then you need to just install the package. Forecast. And once it's installed, this one takes a while. Wow. All right. Once that's installed, load up the library, and then you should be able to just pull in this data set called air passengers, which will already be there. So that's the one we're going to be using today. This command right here should work, just air passengers. And so we should have a new data set called air passengers. I'm just going to be using the 3 letters DAT because I don't like typing as much, so I've just used DAT the whole time. So whenever you get a new data set, again, I always recommend to check out what it is. It might not be what you think it is. So I'm going to look at what DAT is. And it's a time series, as we see here, from 1949 to 1961. Okay. So these like preloaded databases in R, you can always figure out more about them by just doing the question mark and seeing air passengers. And we can kind of read about what we're actually working with. And so it's the monthly airline passenger numbers from 1949 to 1960. All right. And it's a time series already. So the homework you're going to have, it's going to be given to you in a CSV format. And so you'll need to convert it to a time series. I can't really demonstrate that as well here, but essentially you're just going to be doing a time series, and then you put in the data's name, and you're going to have to do the frequency, which the frequency is like how many periods are inside a period. So I think Johnson & Johnson's is quarterly data, so there would be 4 quarters in a year, so you'd have a frequency of 4. In this case, the frequency is already done for us, and we can kind of see what the frequency is. This one is in series of 12 because it's monthly. So if we look at, just look at the data. I don't know what y'all like to do, view maybe. I lost my time series part. That didn't work. You'll see it's January, February, March, April, May, June for 1949. Okay, and we can see what's going on with the plot. And you can kind of see this time series. You all see that? All right. So first off, what can we tell right away from this time series? How would you categorize it to someone? Yeah.
Seasonal?
Yeah, I see some seasonality. What kind of makes you say that? It's kind of the waviness, right? Yeah, the fact that it goes up and down. And that makes kind of sense if you think of airline passengers. There's some periods of the year that have more flights than others. I mean, holidays are usually pretty common. As well, since we see an increase in trend, right? All right. So I think the first questions on the homework, they asked about stationarity. So we should describe this data set as stationary. No, right? And what makes you say it's not stationary? It's a lot more fun with other people talking. Trust me. Huh? Yeah, go ahead.
Is it because it's not constant?
Yeah, just because it's not constant. So if it was stationary, we would just see it just, wave around maybe some number, but it would be about the same. And it also have to be the same volatility. So, yeah. But there is a specific test to be using, and let's pull up the homework. It asks for the augmented Dickey-Fuller test in the T-series package. Okay, so we're going to first run it and then see what is going on. So first off, it said it was in the library T-series. So if we don't have that library, let's make sure we have it. I think it's actually a component of forecast. So if you load up T-series, right, so we got it. And then the Dickey-Fuller test is adf.test. Yeah, augmented Dickey-Fuller test. It's not really obvious, but it's adf.test. And then we just plug in whatever the data is that we want to look at. Okay. So, we have this output here. Now, first off, what do we think the answer should be? We kind of know what the results should be, right? We already decided, is it stationary or not? Yeah. So, this one, all right, so it's not so easy to interpret, but you're going to get a p-value, right? So the p-value is just like any other hypothesis test you do. So what does a p-value mean in a hypothesis test? Yeah, so what's the it in the statistical significance? You're on the right track there. We are testing if it's significant to a certain level.
If it's statistically significant, then we can reject it.
Right. Yeah. So yeah. You can find out more about it also by doing this question mark adf.test. And for a null that x has a unit root, basically we're testing whether the alternative hypothesis, if we can reject the null. So I don't know why this p-value is coming out weird, but that's how you would interpret the ADF test. In this case, I don't know why it's giving me a low p-value with alternative hypothesis of stationary. I think it's because it's trying to, yeah.
So if there's a p-value below that alpha value, would it say that the ADF test is statistically significant and that it is non-stationary data, or is that how you interpret it?
Yeah. So if the p-value is below a certain percentage, you say that you can reject the null hypothesis, which the null hypothesis in this case is confusing because it's claiming that the alternative hypothesis is stationary. So that's why I'm confused because it's saying that it's yeah. When I did it with the homework, I didn't get it as confusing as this. And I think that's the reason why is because that actually looks a lot nicer. And so it's different seeing it. Okay. Yeah, I'm sorry. Yeah.
For the air passengers data, did you use the one from the GitHub, or you just?
No, this is just one. You'll be able to get this if you just do library forecast. It'll already be in R. You don't have to download this from GitHub or anything. It should already be there with the package. Yeah. Just these first two commands should get it for you. And you should be with me. Yeah.
Okay, sorry, just to clarify.
Yeah.
So in this case, because it is below a 0.05 value, we can accept the alternate hypothesis.
Yeah. So this one's claiming it's stationary. I think it's using this lag order. I'm actually not as familiar with this. If this p-value is really high, and that's you'll see in your homework, then you would not be able to reject the null.
Okay.
Yeah.
So in this case, we can reject the null hypothesis.
Right.
That's acceptable.
Yeah.
Thank you.
Yeah.
Do we ever make this a time series?
So it's already come in as a time series, and that's what's kind of saying that in the homework, you're going to need to convert it to a time series, and in this case, it's already done for you. To convert it to a time series is very easy. You just declare something new, and you just say TS, which stands for time series. You put in the name of the data, and then the frequency, and then you'd also put in the start. I would follow along with the question mark TS, and it says TS, you put in the data, you tell it what start time to have, and then the frequency is the big one. And that's it. Frequency would be the number of periods in something. So for monthly data, you'd have 12 periods per year, and for quarterly, you'd have 4 quarters per year. Okay. Yep.
If the p-value is 0.06, then does it mean that the model is useless, or?
No, not that the model is useless. The p-value would represent the probability that you can, that you saw the data given the null hypothesis, right? So if the 0.06 is very unlikely that you observed this under the assumption of the null hypothesis, and so it makes you want to say that the null hypothesis is not true. That's basically what the logic is. Does it make sense? So just whenever you have a low p-value, that allows you to reject the null. So it's important to know what your null hypothesis is. Yeah.
What is the null hypothesis for this test?
All right, and so it's the opposite of the alternative hypothesis. So that's how I'm interpreting this here. So I'm a little confused why it's being able to figure that out. I think because it's using this lag order. So let me think of something that's absolutely not stationary that I could show you. Some stock data. Stock data. I'm getting too complicated. Quickly. Yeah, I'm afraid I don't have a quick example on you for that one. Sorry. All right. So the ADF test, he does do an example on the slides, so I would recommend you just check that again. I'm gonna move forward on that one. I'm sorry, this data set's not a great example of looking at. Yeah.
Could you give us an example of how to change data set into time series if it's not already changed?
I don't have a data set right on my hands is a problem. Let's see if there's something from before. I don't have a data set to convert off the top of my head, unless you know of one that I can use right now.
So essentially all you do is you use the time series,
Yeah.
question mark time series, and use that.
Question mark time series, and that explains it right here. And then you just put in, so I would do like, if I had some new data, I just do time series, the name of the data, and then frequency would be the big one, which again put in the number of periods in your thing. So if, let's say I'm using quarterly data, that would be a 4. And then you don't have to have it, but I kind of like doing it. The start will tell it like what is the start date to start at. So you can start at the second quarter of 1942 if you have that. You just put in 1942, comma 2. And you have to do a C in front of this. Yeah. So I would load some data, I don't know what the data is, quarterly data, and it would start at 1942, the second one. And you don't have to tell it to end, but they'll just go until it stops.
So it's 2 at the second quarter?
Right, so I'm starting at the second quarter in this case. If you want to start the first quarter, you just do a 1. And I think if you don't give it anything, it just starts at 1, too. Okay. All right. So let's move on. Sorry, the ADF test wasn't a good example in this one. So we're gonna do a one-sided moving average, like the homework asked here. So one-sided moving average is basically just you're gonna average the previous terms. And so how many terms should you take? I mean, that's kind of dependent on what the data set is. So in this case, it's annual split up by months. So I'm gonna grab an entire year, and you can kind of imagine what you would do for quarterly data in that case. So for this monthly data, what we're going to do is essentially we're going to grab every period for 12 periods before. So we'll call this air moving average, and it's going to be equal to the data plus the lag of the data from one before it. So if you're not familiar with this lag function, essentially all it does is it grabs the value that was the previous value. So if I just do lag -1 of that, it just grabs the previous months, and if I do -2, it grabs 2 months before. So I'm just going to do that for up to 12 here. So with quarterly data, it's a lot quicker, but essentially -1, -2, -3, -4, and on. 6. Almost there. Okay. And so I'm going to have this error moving average, but it's not quite average yet, is it? What am I missing? Is anyone following?
Divided by the amount of months.
Right. So if I want average, an average is the sum divided by the number of terms, so divided by 12.
For quarterly data, you would just start at -1, -2, -3, -4, and divide it by 4.
Right. Yeah, that would work. Okay. So let's look at what we have here for this error moving average. So if we plot error moving average, we'll see that we have this a little bit more smoothed out line. And it would be more informative if we plot it like this. Let's plot the data and give it a title. When you're turning these in, please have titles for your things of what these things are. And then lines error average color equals green. Okay. So now we'll plot the data, and on top of that, I'm plotting the moving average. So you should get a plot sort of like this. I'll show you the code again. So I'm plotting the data, giving it a title, and then adding a line for moving average, and give it some sort of color. And then you should get some plot like this. Okay. So what can we say about the difference between this moving average line and what the original data is? What sort of transformation, why would we want to do something like this?
It smooths out the trends.
Yeah, exactly. It also gives us like a better idea of like how linear this is, right? It was a little hard to tell before, but I mean now it kind of looks pretty clean, right? So it's good for telling trends. That's what I think a good moving average does. And then the number of terms you are is how smooth it's going to be. Okay. So that's a good looking plot, something I'd like to see in homeworks. And, okay. Did we see any significant peaks or drops in this particular plot for the smooth data? Yeah, not so much on this one, but you could. Yep.
But doesn't the peak and the drop are becoming more obvious later on in the year, later on in the period?
Yeah, perfect. So you see that the actual data, it seems to be up and down a lot more, and you can kind of tell because of how much it differs from the moving average. So that's very observable. Very good. And we'll see that in just a minute here when we detrend it. Okay, so the reason why we do these sort of exponential, these moving averages, is so that way we can detrend it here, so we can sort of see that. So detrending is the idea of to remove the trend, and that way we can see what the sort of seasonality is and kind of what the pattern. You can kind of see it goes up and down, but it'll be a little bit easier once we remove that. So removing it's pretty easy. I'll just call this one D-air for detrended air, and I'll make that just the data minus the moving average. Okay. So if we plot that, we get this. So you just see those sort of bumps now. That's all we have, right? So something like you're saying, it seems to be growing and kind of how there's volatility. Okay. So that's how we create the seasonal sort of model. Now, what sorts do we see that the do we think the trend is additive or multiplicative? And what makes you say that?
Because it's constant, so the variance grows later in the period.
Yeah, so the variance is growing as the trend goes up. That's what makes it say it's multiplicative. And we can actually test out what it is. We can just see what it looks like with both of them. So let me grab, because I forgot how I did this. Yeah.
The variance grows as time goes on?
It's really based upon how the y value changes. So if the y values are growing, that the variance would change. But you can actually have the negative relationship, so it turns out the same thing. Yeah. All right. So we can test out both things. What we did right here was actually the linear, because I said that it's subtracting. If we wanted to do it multiplicatively, we just divide it. So I'll call dr2, which is the multiplicative version, and I'm just dividing it now. And so if we try that out, this looks a little bit more steady, right? So we just tried out both of them, and for additive you just subtract out the trend, and for multiplicative you just divide by the trends.
And you choose the one that's the most like even across.
Right. So we're trying to pick the one that's most even. Okay. This is just the code I used to make it look like a nicer plot. Okay. So I can't really talk about this one too much because it's very specific to the data, but definitely if you're knowing changes that happened, this one didn't have as many. It's interesting to try and think about why it did. And that's really just more just thinking about the business sense. There's not as much statistics there. Just try and think of why that would be. Okay, so the next part in the homework, it talks about aggregating the quarterly data to obtain yearly earnings. So essentially, it wants to move out of the seasonal world where we see the different quarters have different earnings, and into just an aggregate of seeing year by year by year. So you can run this code. It's not really as informative, I think, on this example. So I'm going to leave it as it is. Yeah. So I want to leave it as it is, but you just run this code in the actual homework to do it. So I'm going to leave it as it is. And then the question then asked about regress the yearly earnings on the years and call a linear model. So essentially, we want to make on sorry. Okay, so on this graphic, we see it's definitely like a very linear trend here, right? So the idea is just that let's just try a linear regression. Okay, so we definitely know that there's some violations here in the line assumption. Like definitely independence is violated. It's the main one because it's a time series, and we definitely know that the previous error is related to this current error. So we're going to go ahead and plot a linear regression. And how can we do that? Well, we're going to pull out the time from it. I'm just going to call it time p for time passengers, and it's equal to time function of the DATs. Okay. So if you want to see what time p we just created is, it's just the days in like a numeric version. So it splits the years up into 12 for the months. That's all it's doing. It's grabbing the date basically. And we're just going to regress the number of passengers as a function of that year. Okay, so nothing special. So I'll call it M1. It's a linear model where we're regressing the passengers as a function of time. Okay, and I'm working in different, these aren't in a data set, they're just separate vectors. So unfortunately there's no DAD argument or anything, you just run this. And we can see a summary of the model. And so as you can see, we're seeing that with time it's going up. And then it's a negative intercept, and that makes sense because you're starting at year 19, I forget what the first year is, 1950. Or 1949. We can see how this model is working with abline before. And so we can see how the regression is according to the data. So it doesn't look horrible, right? Kind of looks like the trend. This one looks a lot more nice, linear, but of course you need to check how well it's fitting, and you can do that always with just plot the model. And when I use that and go through its little cues, you'll see the residuals versus fid. So this one kind of shows a little bit of heteroscedasticity. That makes sense, right? Because we saw that the volatility was increasing as we went forward in time, right? And also, if it was nonlinear, this one looks a little bit nonlinear. It's not that bad. When you do your homework, you might notice it being more so. So you can flip through the other plots. You all know the QQ. This one doesn't look too bad. And then I don't worry too much about these other ones. Okay, so linear model works really well on this one, but as you can tell, it asks for years squared, so it might not work as well on the next one. So I'm just going to go ahead and run through how you would make a quadratic model on this. Essentially, a quadratic model is just that you're imagining it's a quadratic fit. So how you fit sort of quadratic, the curve to it. Well, you'd add another variable that's just time squared. So I would have, I'll call this the quadratic model. I'll call it time p2 for time p squared, and I'm just going to square time p. And you can square it by just doing 2 stars and a 2 like that. Okay. And I'm going to call it m2. Do a linear model of that as a function of time p plus time p2. You need both of them. You don't do a quadratic without the linear term in it too. And then when I run that, we will have a new model. So we can look at the summary of M2. So this time it found them both significant. And we can you can plot it with the curve. I'm not going to do that right now, but and then of course you can plot the model to see if it's a better fit. So if I plot this model, we see that it's a little flatter. It's still heteroscedastic, and that makes sense because transforming an x variable doesn't fit heteroscedasticity, if you remember that from transformations, right? So, yeah.
So why would you do time p plus time p2?
So in this case, the linearity is not that bad, but I'm kind of going over this because the homework is obviously a problem considering that next question asks for you to do a quadratic one. And so I'm just writing how you would create a quadratic model in case anyone's confused while they're doing it. In this case, I don't think a quadratic model is necessary, but you'd add time p2 if you wanted to get that curve.
But whenever we used to normally do like a quadratic model, didn't we just do the data versus just the squared version of it?
So if you just do it like this, you're saying? I'm not sure if this works, but if it does, then go for it. So you're doing like this.
Well, I thought that's what we did. Or just time p2 by itself without.
Oh, time p2. So that won't work as well because it won't have a linear term. So let's say we'll call it M3. Right? And if I look at the summary of M3, see, it only has one coefficient now. So it's like now it's no, it's no markers. Fun. So before it was, the first one I did was y is a function of the intercept term, we'll call it b naught, plus some coefficient times time, plus b2 times time squared, right? So that's why that's the first one I did. And if you don't put in the time p, it's like this, but yeah, without this part. And so if you imagine about how you can transform a quadratic, you have your quadratic, right? I'm trying to make it with my mouse. Doesn't work. And when you change the coefficient on the quadratic part, you're basically just like tightening and widening the quadratic, right? And when you change the intercept, you're just lifting it up and down. But you have no way of changing it horizontally. That's why you need that linear part, so you can have that transformation too. Yep.
When assessing the heteroscedasticity in the plot, how does it make sense?
Oh, okay. So the reason why I said it seems logical to me is just when I plot the data by itself, you kind of know this earlier that the seasonality effect is increasing, right? Because it's multiplicative. And so that could be the same thing as your volatility. Imagine you draw this line, right? So I'm more accurate over here because it's not jumping up and down as much as I am over here.
And then you're mentioning that it's related to the transformation.
So what I was saying is that we're not going to fit heteroscedasticity with the transformation we just made, because we transformed the x variable. And if you remember from transformations, whenever we transform, if we want to fit heteroscedasticity, we have to work with the y variable. Okay.
So would it basically violate the linearity, the heteroscedasticity, and the normal?
Yeah, so we're violating a few things here. We're definitely violating the main ones, the independence, because we're doing it on a time series. But that doesn't really affect the, if we're just trying to detrend it. It's just a matter of what you're trying to do, right? And we're definitely violating the heteroscedasticity. But both of those actually only affect your standard errors or how well you know your coefficient. And we're not doing any assessment about like how well do we know what the trend is. So in this case, it's okay, I think. Yeah.
So the violation of the heteroscedasticity is not as important as the others?
I mean, they're all important. It's just important to remember what the implications are. And so the implication would be that I can predict better over here than I can over here. You know, which isn't really telling me too much because I'm not predicting anything in this range anyways. I'm predicting outside. So just kind of tell you that, like, if I just use that linear model, it's going to say I'm more accurate than I am if I'm trying to predict further out. So, I mean, it's good to think about, but yeah. I'm glad you asked these questions. Okay. So is there any questions about creating these linear models? Which one, by the way, even though I don't think that the square term is very informative in this case, because it seems to be a pretty linear model, which one's going to have a better R squared? Which one's the first one? You're saying this?
The B none plus B1 times B2 times.
This one right here?
Yeah.
Yeah, this one's going to have the best R squared because it has the most predictors. So you can't decrease R squared whenever you add a predictor. Okay.
But wouldn't the one on the bottom would have been, since it's simpler, then wouldn't it have a better adjusted R squared?
Yeah, I think that this one probably, excuse me, this one right here probably has the best adjusted R squared. We can look at 0.8526, 8599. Ah, all right. Well, it still worked out that P2 in this case had better, but okay. So moving ahead. Okay, so one idea is the fits the stationarity issue is differencing, which is essentially just like, well, we just model what the change was from the previous one every time. So that kind of makes sense for a lot of things because usually if I don't know anything new about, if someone asks you how many sales am I going to have this month, I mean, the first question, the most informative thing would be, how many sales did I have last month? You know, that's kind of the way you usually go. So kind of the idea of differencing is we'll just look at how the changes are. So that way we'll start at 0. You assume that things are around there. So to difference, the main way we teach in this class is that we'll just say, I'll call it del for delta. The change in passengers is just the data minus the lag of it, right? Actually, I'm not sure if that works. Let me see if that works. Let me double check. Yeah, it should work. All right. So that's the way, that's basically just all we're doing. We're just taking the previous value and we're subtracting that. Another way you can do it is just this function called diff, and that will do exactly what it is because it's a very common procedure. So that's one way of differencing, but the idea is that we're trying to make this stationary. So now if we look at this del, so let's plot it. Is centered around 0 more, which makes sense that the actual change is around 0. But because it's increasing, I don't think that the average is going to be 0. Does that make sense? Like if it's increasing, the average change is still going to be positive. Does that make sense? Okay. So this is what this is the change. So like this would be 1950 January would mean how much did January have that 1949 December didn't have? So that's what we just did. We differenced it. And so it's going to be a lot closer to stationary, right? Like we're just doing the differencing here, so it's not like just going to grow over time, ideally. But still, the average is not going to be 0. And does that make sense why it wouldn't be just 0? Because if the average difference was 0, then this wouldn't be growing over time.
If it was cyclical, would it be 0?
If it was cyclical? Yeah. So by cyclical, you mean like the... Yeah, so we're starting to see the cyclicalness because you can kind of see it here that like, so now if Decembers are always our high period, then the difference of December from November is always going to be high. But it's more like the overall trends. Yeah. Okay, and so what I'm saying is that if I look at the mean value of del, that's not how you do averages. It's 2.237. So that's like the average increase from the previous one.
Wouldn't the difference, is it true to say that the difference is increasing as time increases because of the unequal, because of like seasonality, like how it keeps?
Yeah, that makes sense. So that'd be like more of like exponential growth, right? If it's growing at a faster rate over time. And yeah, that's something to definitely look out for. That'll be something that's kind of.
So is that what that shows?
So this one I don't think as much. I do think the volatility is going up because I think I still could draw like a line that would be approximately like this, right? But the changes between each season is definitely increasing. So I think you're right. Okay, so you can run the ADF test on that thing again. I don't think it still don't just say it's stationary, but. You'll probably note that the p-value gets really small because now I think it's even more stationary than it was before. So that's mostly what you're trying to test. And the idea of doing these sort of differencing, there's a lot of different ways to difference. This is the easiest one, just like a linear difference. But like one that's really common with stock data is to take the logarithm and then difference that because things change more like proportionally. So you do the logarithm to take care of that. There's a lot of different ways you can difference. The idea is that you make some sort of transformation to make it stationary because these ARIMA modeling that we're going to do in a second here, it depends on that. Okay, so next we're going to plot the autocorrelation function. And so what autocorrelation means is this increase related to the previous increase, or maybe it's related to an increase 12 periods beforehand or 6 periods beforehand. And so what that is just ACF for autocorrelation function, and then the name of the data set that you're interested in. So what this does, what this is the lag. And remember, lags here are in terms of a year of what the change is for the previous one. So we see that we're positively correlated to the previous lag. Okay, so what that means is that if we saw a high value yesterday, we anticipate that we'll have a high value today. Okay, so that's the positive ones. That means it's above here. And if it's negative, then it's the opposite relationship. If you have a high value on that time, then we'll anticipate having a low value this time. Okay? And so to me, it makes sense that years are highly correlated. Because if I'm trying to do like December of this year, I think good information would be, I get some good information from seeing what was my sales, my passenger data for December last year. And same thing for November to November and such. It also seems to detect kind of an interesting correlation here. It looks like 1, 2, 3, 4, like 4 months beforehand. And I'm not entirely sure why, but it seems like it's almost like kind of quarterly. Yeah. That's what's going on there. And the big idea of using here is that these little dotted lines here is kind of the idea of what is significant. So if it's within this dotted line, I mean, yeah, there's a little bit of negative correlation here, but we don't think it's significant. If it's past the blue line, that's kind of the sign. Okay. So why do we do this? Well, one, it's kind of informative a lot of times to see kind of the cyclicalness of looking at these correlation functions. Because this just told me, like, I mean, it makes a lot of sense in business world that, like, yeah, the December data is going to depend a lot on the December data beforehand. But coming into some other thing that you don't understand, it can be kind of informative. And so the idea of making these auto regression, you know, prefix auto just means on itself, is that we're regressing the data on itself. So we're going to regress the value now on like what happened yesterday and what happened 6 weeks before. So what periods should we grab? Well, we get that from this chart here. If we found that a full year ahead of time is significant, we should probably include that in the correlation function. Okay. So this one has a lot more periods, but stock data is usually a lot more volatile, where you're going to have a lot fewer things to regress on. So I'm going to do 12 and 4. I think that's why I found a pretty decent model. And so I'm just going to include those lives. I'm going to regress the data on its previous self from 4 terms, 1 term beforehand, 4 terms ahead of time, and 12. So this one, and this one. Okay, so I need to make this data set with the 4 and 12. Actually, R has a lot of functions that just automatically do this sort of stuff with you, but we're going to walk through like how you do this like he taught in class. So I'm going to call, what am I going to do? So there's this function called cbinds that just means column binds. And it just combines R objects by columns with the C one. There's R bind for rows. And so I'm just going to cbind, I'll call this AR data for R regression data. It's a cbind of del and a lag del by -1. So that'll be the -1 term. And then the lag del by -4. And a lag del by -12. So from 1 month beforehand, 4 months beforehand, and 12 months beforehand. That's what I'm grabbing. Okay. And so I basically just, just display this. So you can see here that the sits, and the sits is just kind of go down by 4 months. Yeah.
Can you say how you got the 1 for 12?
Yeah, so that's what I was talking about here. Is that it's kind of hard to see. It's a little bit easier with fewer periods. I mean, quarterly is kind of a little bit easier. But this is, the first one's always going to be 1 and it's 0, because it just means that the data is correlated with itself perfectly, which is obvious. So I don't know why it includes it. And then 1 term beforehand, we see that it has a significant correlation. and I counted 1, 2, 3, 4. So I wanted to grab this one, and then for more demonstrations, I did 12. I mean, really, all these looked pretty significant. 1, 4, 5. This looks like 8, and so you could grab all those if you wanted. But I thought for just teaching, we just do 4 right now. And so ideally, you grab whatever shows significant on this autocorrelation.
So you want to pass the blue line.
Right, blue line is significant. Yeah.
So what is on the y-axis here?
Y-axis, this is autocorrelation.
So is that the
So it's correlation, just like what you learned in the previous class, where if I did, I'll demonstrate this a good idea. So if I ask for a correlation between the data and the data from one before. Oh, that's not very good. Yeah, I have to tell the time series a little more complicated than coding. What? No, this is the one the previous one. But they'll show it for this one too. Yeah. Oh, but I have it bounded now. I'm doing the right function, right? For AR data del AR data one. Sorry, I'm gonna have to think about how to do that. Yeah, sorry. So I have this data set which is just a column binded. So it's just I put them all into one data frame, so that way I can do the regression nicely. And I'm gonna change the names actually. Our data.call names. Del. Flag 1. Flag 2. Or 4. 12. I'm just giving it some bare names. And then we'll call this AR linear model 1. And it's just going to be a linear model where we're regressing del as a function of its previous value plus the value from 4 months ago plus the value from a year ago. Sorry, troubleshooting here. Change column names. Sorry, I wanted to change the column names, that way you can regress it. Change. Oh. Yeah. It's not dot column names, you have to do call names AR. So I'll change the column names, that way this will work. And if we look at the summary of AR linear model 1, we see that not a lot of things are going to be significant. That's kind of something that happens with these AR models. It's pretty tough to get perfect regressions from it. And you'll see that the annual data is just what's really driving it. You know, that makes sense that like the December from previous year tells us a lot about the December of this year. So you can do that with all the significant ones. One of the tricks is that ACF is autocorrelation function. It's a little bit tricky how these work. They make these kind of waves. And what kind of, in my practice, kind of works better for telling what's good is something called PACF, which is the partial autocorrelation function. And this one tells you, I feel like, a little bit better. I bet that if we did 10, 8, and 12, it would be a lot better model. But we don't need to go through that. But that's what we're doing with these regression models. We're just regressing the data against itself a few times before. Okay. I think we got one last thing. I'm running out of time. So simple exponential smoothing. Okay. So it's a nice function, just SES, and that just stands for smooth exponential smoothing. And we can do it with any data set that we imagine. So we're going to do it with the data, and I think in the homework you're doing it with the annual data. So I'll call this SES 0.25. And so simple exponential smoothing is kind of like the moving average, but we're grabbing all the data points beforehand, and it's just like an exponential decay of how far. Because we imagine that like the previous months are going to tell us more about, like the more recent data is going to tell us more about the next data more than the old months, right? Last year's information is way more valuable than information from 10 years ago. That's kind of the concept of it, and it's just the exponential decay of what's going on. So the function SES is simple exponential smoothing, and so we can make one for 0.25. Let's say that's for the alpha we're going to use. And alpha is like the rate of decay. And so you'll see what I mean in a second here. I'm just going to do it for 3 different alphas here to kind of demonstrate. This one for 0.50, and this one for 0.75. Change these as well. Okay. And then, because I'm running out of time, I'm just going to plot all these for us. There's not too much hard code here, just SES, simple exponential smoothing, and if you give it an alpha parameter, it will use that alpha parameter. So I'm fitting these 3 simple exponential smoothing, and then I'm going to plot the data with the fitted lines. Okay. So the black line, it's going to be pretty tough to see. I'm doing too many at once. The black line is the actual data. Okay. And so this blue line is the lowest alpha. And so you see that this blue line, it's flatter, right? It's smoother. That's because the rate at which we're decaying the function is slower. So it's taking more weight to the far previous values. The red one is the largest, and that one is the most responsive. It's pretty much just taking what the previous value is, and that's it. So that's all that's happening there. And so the red one you'll see is much more spiky, like it follows things really quickly, while the blue is a little bit slower. It's kind of the idea. And you'll also note that exponential smoothing will always be one thing behind. You see how this peak's right behind this peak? That's because it's just basically just chasing what happened before. Okay. So we don't have to figure out an alpha by ourselves. It will do it for us if we just don't tell it an alpha. So just do SES and don't tell it an alpha. And if you want to get some information from it, we can look at the summary. And you'll see here what alpha parameter it shows. It shows a very high alpha parameter, and it bases that on, you remember the AIC. That's how you see which alpha value to use. Okay. Now what if what should the forecast be using this simple exponential smoothing? So I'm just running out of time here, so I'm just going to plot it. You can try it out for yourself, but if you just plot the simple exponential smoothing, it plots the exponential smoothing, what it forecasts with the data, and then this blue line is prediction. So it's flat. And why do we think that is? Remember how simple exponential smoothing is. It just takes the previous value and the average of all the values before. So if I'm predicting 1 forward, what would the prediction be for tomorrow? It's just yesterday's value with the other one's averaged in, right? And then what about the value after that? Well, it would be just the value I've just predicted plus all the ones averaged before that.
So basically, it's like it equalizes at the end.
Right. So it's just going to be a flat line because it doesn't predict any trend. It's just taking the previous value is really all it's doing. And so if you just take the previous value, you're never going to change, right? So the value is going to be the same for the end of time with the way it works for forecasting. Yeah.
And you mentioned adding the averages from the previous years or previous.
Right. So it does also average all these values beforehand, but they're all decaying at the same rate. So you can try out the math a little bit. Hang around, I'm kind of running out of some time. But essentially, it comes out to not changing anything. Okay. So yeah, that covers everything there. I will be posting this video. And so in summary, we discussed quickly how to make a time series object with just that TS function. And if you need more details on that, just do $TS. But you just put in the data, the frequency. Testing stationarity was kind of flown over because I didn't have a good data set for running that. But the ADF test, remember that you're just a low p-value means that you have enough evidence to reject the null. So see what your null is and you can reject it or not. The moving average models we did by hand. Basically, we just averaged the last so many terms and it allowed us to find out what the trend is. And from that trend, we removed it. And we can do either additive or multiplicative. You can see which one it is by which one's more stationary. And divide for the multiplicative and subtract for the additive. Annual data just mostly follow the code that's just posted, but you can use a linear model with predicting with time. You difference to try and make stationary, so we can do these sort of autocorrelation functions. And you can difference just by using the lag. I think the diff function is really quick, just DIFF. ACF is the autocorrelation function, so you can see how the data is correlated with itself. And then you just regress its previous values. And finally, we just had simple exponential smoothing, where you can try out different alphas. The homework has you try 3 different ones, and then you can have it automatically pick one by just not telling it. Okay. Thanks for attending. No problem.